Hi everyone, welcome to another video for research design and analysis. This is our second in our series of videos on models with repeated measures. And today we're going to be talking about repeated measures ANOVA as kind of an extension of what we did in the previous video where we were talking about the dependent samples t-test. So repeated measures ANOVA is conceptually very similar to what we've done with factorial ANOVA before, where we're going to have, some kind of categorical predictor that has two or more levels to it. But the difference is that now, rather than having different people in separate groups, we're going to have the same people exposed to different conditions over time. So for instance, let's assume we're looking at some kind of learning or training study where we're measuring people's performance with a skill at 3 months, 6 months, and 12 months. In these data, it could look like we have 9 different time points here. And it's really hard to tell if there's an effect on performance here that is reliable if we were just looking at these 9 different time points. However, if we recognize that these are actually repeated measures from within the same person over time, the improvements in performance become more clear. The overall pattern is a little fuzzier, but if we look at, okay, well, these are the 3 time points from subject 1, we can see that subject 1 is reliably improving over time. These are the data from within subject 2. Subject 2 also seems to be reliably improving over time. These are the data from subject 3, although it's a little more modest, they also do appear to be improving over time. So by identifying repeated measures within subjects, that shows us the quote-unquote true or a more accurate effect of the training protocol. The issue here is that the variability within subjects is relatively small, right? People are making modest gains in this task over time, and it's especially small relative to the between subject variability. So it would be really great if we could remove this between subject variability in much the same way that we did with the paired samples t-test. Now it's going to be a little bit more complicated here when we're talking about models or where you have more than 2 levels, but it's conceptually the same. Much like in the dependent samples t-test where we had to control for what your average level of performance was, we can now control for the average level of performance of each person and then say, it's no longer what was the absolute value of your score here, but it's were you low relative to yourself at 3 months, and then were you high relative to yourself at 3 months. So by calculating what each of these means are for each subject, and then removing all of those means, right? So now everyone is kind of centered around 0. We can more accurately say, well, what was the effect? What was the change in performance over time? So it's going to be a little bit more complicated in how we do this relative to doing this with the dependent samples t-test. And we're really going to drill into that in the next video. But conceptually, the thing I want to impress upon you is that this is basically the same. All we're doing is the same process as when we had a factorial ANOVA, because we have a categorical predictor, which in this case has 3 levels. Right? And we want to calculate an omnibus F-test to say, was there an effect of time here? The only added wrinkle is that before we can calculate that F-test accurately, we have to remove the variability due to which subject you are. So if we can account for your average level of performance, pull that out of the error term, then we can more accurately calculate what variation is explained by our effect relative to the residual variation that remains to be explained. So by partitioning the variance into those different sources, right, the variability explained by the effect, the variability due to which person you are, and then the residual variability that remains, we can more accurately test the effect of time, calculate that omnibus F statistic, and then we can calculate a p-value in just the same way that we did when we had independent data, right, and we did a factorial ANOVA. So now we're doing the same thing, it's just that we have repeated measures within a person, so we have to do a repeated measures ANOVA, and we have to account for data coming from the same person over time.